We are now going to start the first session today on the fish health. I invite the chairs of the session, Dr. Stephen Pycroft and Dr. Parvata Kumar Pradhan, to kindly come on the dais. I also invite today's keynote speaker, Dr. Andrew Shin, the lead presenters, Dr. Sonal Jayesh Patel, and Dr. P.K. Sahu to occupy the chairs on the dais, please. For this session, we have session coordinators, Dr. Makesh, Principal Scientist from ICR SIBA, and Dr. Anirban Paul from ICR SIFA. I kindly invite them to coordinate the session, please. Today's chairperson, Dr. Stephen B. Pycroft, is a senior lecturer in veterinary pathology at the University of Adelaide. With 38 years of veterinary career, he has extensive experience in diagnostic pathology and animal disease research. His research spans a wide range of areas, including stem cell studies, the development of clinical biochemistry reference ranges for southern rock lobsters and Pacific oysters, and black soldier fly production for fish nutrition. A strong advocate of evidence-based science, his passion lies in advancing aquatic animal health and promoting sustainability. Dr. Pradhan, the chairperson for this session, is currently serving as a principal scientist and head of exotics and animal health division at Indian Council of Agriculture Research, National Bureau of Fish Genetic Resources, Lucknow. He has over 23 years of professional experience, including 17 years in research and 6 years in academics. Recently, he has been designated as WOHA expert on infection with Aphanomyces invandens. Welcome, sir. Now, I request the chair to kindly coordinate the session, please.
Well, good morning, everyone. Hopefully you slept all right and you're keen from a good day of technical sessions. It's my privilege to introduce to you our first speaker, Professor Andy Shin. He's a global technical expert at Benchmarks Advanced Nutrition, INVE, specialising in disease management. With over 35 years of experience spanning diagnostics, biosecurity and welfare, Professor Shin has made transformative contributions to aquaculture across Asia and beyond. He is a co-founder and overseas director of the Fish Museum and Biodiversity Centre in Mymensingh in Bangladesh, and is an invited member of the network of aquaculture centres in Asia Pacific, NACA, Asia Region Advisory Group on Aquatic Animal Health. He has a PhD in Veterinary Aquaculture from the Institute of Aquaculture, University of Stirling, Scotland, and the Natural History Museum of London. A prolific researcher with more than 190 peer-reviewed publications, he has also held honorary academic positions in the UK and Australia, and actively advises international bodies, including FAO and OIE. Without further ado, welcome, Andy.
Thank you very much. Good morning, everybody. I'm very excited to be here. And just before I start, I would like to say a huge thank you for the organisers of DA12, but also to the Asian Fish Society and to all of you for coming this morning. It's lovely to be here. So today, what I'd like to do is I would like to take you on a small journey. So I'm going to be talking about the hidden $1 million burden quantifying Asia's aquatic disease crisis. But what I would like to do is to be a little bit challenging, give you something to think about. It's going to be a very simple, very gentle talk. But really what I'd like to talk about is I want to take you on a journey beneath the surface of Asia's remarkable aquaculture success. And I really want to try and reveal a crisis that's costing billions and is threatening the food security of millions. Okay. So when we go to markets, this is perhaps the thing that we're all familiar. We see the success of production. We go to a market, we see beautiful, wonderful range of fish being sold, competitive prices. It's offering a wide range. What we don't see, unfortunately, behind this success is, unfortunately, we don't see the abandoned farms. We don't see, for example, the abandoned ponds. We don't see the crisis behind some of this success and the millions that are being lost, perhaps, to disease. So For those of you that know me, you know I'm a parasitologist. I'm pretty passionate about parasites. And just a month ago, I was working in a fish pond, and as I was collecting my water samples, collecting my fish samples, I also found that I'd actually attracted a few little friends. Yes, I'd actually picked up a few leeches. And you're probably familiar with this. This is an occupational aquaculture leg, or as we call it in the business, this is leechy leg. And so this kind of, the irony of this really wasn't lost on me, but what it struck home is that we're all working in the same environment. We're farmers, we're growing our fish, we're parasitologists, researchers, working in water, but so are the pathogens, so are the parasites. Okay, we're all part of that same environment. Just a quick comment before we go on from this. If you do pick up any leeches, the first thing to do is to take a credit card. Don't squeeze the leech, because if you squeeze the leech, you'll actually cause it to vomit into your wound, and that can cause problems. But just take a credit card. It doesn't matter, American Express, Visa, MasterCard. The leeches are not particularly fussy. No platinum card or gold card is perfectly fine. And then just take that card, just slide it underneath the leech to release it, okay? That's my innovation as part of this transformative innovations workshop. Okay, so we already heard this yesterday from Dr. Mohan. We see that Asia has aquaculture dominance. We heard that the figure of 91%. I want to add the 91.92% in terms of the amount of aquaculture product that is produced out of Asia. And you can see here that this isn't just about market leadership, but this is complete dominance in a sector that's feeding hundreds of millions of people every single day. And we see that from a whole variety of different systems, from rice fish systems in China right through to the shrimp farms, for example, in India. Okay, and I think this is the success story that everybody sees. I mean, we know that Asian aquaculture has delivered on every promise. It's delivered a diverse range of species to suit everyone's, the global tastes. It's making protein accessible to the growing populations, but it's also generating export revenues, which boosts national economies. But what you don't see, unfortunately, this is the scene we don't see. Unfortunately, behind all these success stories, there is a mounting crisis. And we can see that the costs, for example, of things like disease, this is really threatening everything that we've celebrated. So just very quickly going around the board, we're seeing here, this is harmful blooms in Thailand. This was a pretty impressive fish mortality. We see iridiovirus, for example, in Korea. We also see, the video's not playing at the bottom, but that's a streptococcus outbreak, for example, in Vietnam. So we have to really think beyond mortality. We have to think about the ripple effect. And when we think about, for example, the actual mortality, we're really just talking about the tip of the iceberg. But of course, we also have to think about, for example, the treatment expenses. We also have to think about the production delays. We have to think about the disrupted supply chains. We also have to think about, for example, how those disruptions then have impacts, for example, on the pricing, which is not just a matter of days or weeks, but those pricing disruptions can occur for months. And then, of course, we also have to think about the impacts not only to the farmers, but also to their livelihoods and to the communities that are dependent upon the culture of some of these fish species. Okay, so in preparation for DAA, what I did, I started to actually look at some of the different industries. And what I've done here, I hope you can read this, but we will take a closer look at this. What I did first of all is I just ranked, first of all the industries by the size of their production. So what you're looking at here, on this slide here, this is the top 46 industries producing over 100,000 tons of fish. Okay, so the top 46 here. So I can just show this a little clearer here with the, there we go. And so this top 46 is accounting for something like 57.6 million tons of production, and this accounts in itself for just over 90% of all fish aquaculture. And if you just want the bottom figure, just in 2023, global aquaculture production was just over 136 million. That just sets the scene. So what we're going to do is we're just going to look at these top 10. So these are listed here. Just to explain the figures in yellow, that's just to show Asia's dominance of the sector. Those in blue, we're perhaps not so interested in, but you can see the top 10 here is dominated by carps, tilapias, various cyprinids, and then we have Atlantic salmon at number 10. So we're not going to worry about the Atlantic salmon. Okay, so let's think a little bit more about this. So what we can now do is we can now organize those top 46, and very simply, what we've done is we've just grouped them by freshwater, by brackish, and by marine water production. So we're only interested really in these yellow figures. I'm not sure, something's gone wrong with the slides, but what you're looking at here, this top 34 here, I've lost the figures off the side there, but it's counting for significant amounts of production. It's actually accounting for something like 93% of all freshwater fish being produced, okay? So pretty impressive. We're not going to worry about the brackish production, and we're not going to worry about the marine production, but there you go, the figures there are at the bottom if you're interested. Okay, so just moving on. I think in some ways we've got it a little bit wrong, for example, in aquaculture. When we think about, for example, the impacts of disease, we think about those one particular disease impacts which is costing millions and millions. But what we have to think about is we have to think about all those small amounts of production that are lost. So, for example, take a 2 to 3% loss, for example, of some of your stocks, perhaps due to some of the parasites that you're seeing here on screen. And really, this is a death by 1,000 cuts, because if you add up that 2 to 3% production there, but you then add it up over the thousands of farms producing millions of crops, then actually the collective value of some of those particular disease events far outweigh the massive mortality event that usually grabs the headlines. So I'd like to think, that really we have almost like a fatalistic acceptance, okay? We almost ignore some of these smaller losses, okay, which are frequently reported. So I think we need to take aware of these, be aware of these and consider their impacts. Okay, so just looking at aquaculture production, here we're just focusing only on fish, but you can see fish production has begun to slow. It's currently increasing at a rate of something like just over 3% per year. And again, just looking, you can see it's quite an erratic kind of growth. It's not the kind of smooth growth that we might expect. And you can see we even have certain dips which are cause for concern. And these are the kind of things that we want to focus on. But of course, as we move into this intensification trap, what we're really doing is we're competing for resources. We're pushing in fish at higher stocking densities. We're fighting for accelerated production growth, not just only in fish, but also in shrimp as well. And we're really cost-cutting on health management, okay? It's all really about prioritizing these kind of short-term profits over biosecurity. And what we're really doing is we're setting ourselves up for this perfect storm of pathogen emergence and spread. Okay, so just focusing on those top 9 species that I showed on that leaderboard. What we're looking at now is we're just looking at production over the last 25 years, okay? So again, you can see this is just the percentage change in production from one year to the next. And you can see it's not a smooth growth for each industry, but you can see it's quite erratic. Some of them, only 1 or 2 of them are actually going up. Some of them are going down. But the interesting thing here is when you start to look a little closer at these, you can see that some years we're actually moving into negative production, okay, where the production has dropped from the year before. And most of these points highlighted in red here, most of these are probably due to disease events, okay? And these are the kinds of things that we're interested in trying to look a little closer at. Okay, so a few years ago, I gave a talk in 2018 talking about different diseases. I tried to rank the top 100 diseases, and I used to like to think of these actually like a kind of like a football league table. I had various pathogens, moving up the leaderboard, moving into the Champions League. I had other diseases falling down into the relegation zone. But you can see that as we go from season to season, like in football, Every season is different. We have different pathogens moving up and down this league table. Some pathogens suddenly appear, they're very ephemeral and then disappear. But also we know that diseases and the various pathogens are also affected by many different factors. So one question I actually had was, has this leaderboard changed, perhaps since I first presented it in 2018? So this is the leaderboard that I presented then. Please don't try and read the details. I will go through this a little clearer as we step forward. But this was the full list that I presented in 2018. Okay, so to try and do this and try and move to some updated estimates, the first thing to do was to try and dive into the literature. Okay, so first of all, just to try and revisit some of the cyprinid data. So a few reasons for doing this was to really just sharpen some of our estimates. It was to go beyond perhaps some of the small samples that we had considered before. Before we looked at 500 disease cases, really we wanted to go beyond that. So we really wanted to try and cast the net a little wider, try and focus in on each individual species, try and fill some of those gaps, try and build a little bit of confidence about some of those estimates that we were building. And again, just a few more reasons there in trying to set a bigger picture and really just trying to move towards some clearer estimates. So the first thing is that was to dive into the literature, and Professor Chanarong and I have one PhD student, Jarul, and we thought that it's not really particularly crazy to ask your student to do a larger literature search, because when a supervisor suggests it, we all know that it's a very good idea. So that's what we got Jarul to do, and really it only becomes madness when you try and do this task yourself, and then you begin to realize just how enormous that particular task was. So 3 weeks ago, preparing for DAA 12, that's exactly what I thought I would do. So Jarul, first of all, very bravely tackled 6,000 cyprinid abstracts. I wanted to have some sharper estimates for looking at the tilapia industry. So I looked at 21,000 abstracts just in the last 3 weeks, myself and Oi, who's also a co-author on this. And that's really when we realized that was the insane part, okay, really trying to do this just because we wanted this sharper picture. So this is taken from Jarul's PhD. This is the slide before was a paper he's got in progress. This is, again, please don't try and read the details. This is just to show that from the 21,000 abstracts that we looked at for the Nile tilapia, the heartbreaking thing was that 21,000 only came down to 4,000 natural events, because obviously we had lots of repetitions, lots of lab studies. And again, when we looked closer within that 4,000, that then distilled down only to 661. So all this effort just to get to 661 disease cases where we had actually mortality reported. So what we can do, at this point, we had to try and start thinking about some assumptions in trying to estimate annual losses. And at this point, this is where I look for Ed Peeler, because this is something that I know that Ed does very well in very logically setting some underlying assumptions. I didn't have a chance to speak to Ed before I prepared this particular talk, but these were the assumptions that I set for this particular work. First of all, and this is the big assumption, that we assume that disease takes account of a loss of about 30% of production. That was the first thing. The second thing was thinking about the reporting bias. So what we had to think about was we had to assume that all pathogens had an equal probability of being reported in the literature, okay? Perhaps there's a little bit of bias there, because perhaps only the bigger events really get reported on rather than all diseases being reported. But we also had to think about, for example, that many pathogens typically are multifactorial. So in this particular case, we really could only focus on the top particular pathogen in each particular disease case. And then the fourth assumption that we had to say was, okay, if we take all those diseases reported in the literature, then let's assign those proportionally within that 30%, okay? So some very broad sweeping assumptions being made there, but as I said, this talk is about stimulating debate. You might get angry, you might agree, but hopefully we will stimulate some debate from this particular talk and move forward with these. So just looking at the key summaries, shall we say, from first of all from Gerul's work on the cyprinids and from the Nile tilapia. All I've done there is I've not put all the diseases, but I've just listed them, just a few of the main diseases, the big hitters, just so you can see how they compare side by side. So again, please don't focus on the detail, because what I'm going to do now is I'm now going to try and combine those. So what we've done now is we've just taken the cyprinids and we've taken tilapia. So again, we're just focusing on those top 9 freshwater fish species being produced in Asia. And again, we can just rank them out. So what we've got here, this is my Football League of 2018. I've removed all the marine and brackish parasites, just focusing on the freshwater. This is the new league of 2024. Again, I've just listed them by the value of the impact. And just very, very quickly, just running down the board, you can see, for example, Argulus has dropped from 6 million down to 1 million. The initial estimate here was probably because at that time, Argulus was estimated to have a 19% impact on the entire cyprinid industry. Perhaps with a little bit of revision, we're seeing that it's still pretty major, probably only 1 billion, but perhaps much lower than the 6 billion initially reported. When we look at things like, for example, Aeromonas, you can see perhaps arguably fairly similar, 700 to 960. So you could argue that perhaps fairly similar given the growth of the industry over the last 5 to 7 years. Again, looking at others, Streptococcus, again, perhaps the numbers have dropped, but you have to remember here that A. galactii is, and this is where I may attract some comments, but I like to think of it more of a marine parasite pathogen than perhaps freshwater. And also Streptococcus ineae can infect both freshwater and marine. So it's perhaps not surprising that these figures only for freshwater are perhaps lower than those that I'd set in 2018. Looking at a couple of others on this board, then we also have, for example, ick. The ick numbers seem to have gone up. Perhaps I underestimated those in the earlier estimates. So I'm fairly comfortable with those, but what I'm not comfortable with is we can also see, for example, some of these pathogens, for example, in a minute I'll talk about the Myxobolus, but the interesting thing about this table is that we now have some new leaders on this board, okay? So you have koi herpes virus, we have koi sleepy disease, and we have HN at the top there as well. As I said, the one thing I'm not particularly happy about perhaps is these Myxobolus infections. These seem way too high for me, and I think these are really worth further investigation because I'm not quite convinced that these particular diseases are causing the size of losses that we see there. One other interest for me is the appearance of Lactococcus on the board here. I'll explain in a little bit why this is particularly very interesting for me. So just moving very quickly, thinking about climate change. This is climate change over the 1960 to 1990 reference period. We all know that climate change over the recent period has risen by 1 degree. Just moving forward, if we look at that 1961-90 reference point, but then look at the temperature in some of the major aquaculture producing regions in the decade before. The good news is you can see we've got lots of blue, lots of light green here. This is good. This means that we're below the reference point. If we begin to step forward to where we are now and look at the current last 30 years, you can see that some of those temperatures are beginning to change. In actual fact, even though average global has gone up by 1 degree, it's probably gone up by about 1.3 degrees over those aquaculture growing regions. And you can see for some places like Turkey and Greece, they've actually gone up over 2 degrees. And really this is a crisis in waiting for the industries in those particular countries. If we start to think about combining, shall we say, the size of aquaculture production together with some of the countries most at risk from climate change, then again, this picture is perhaps not surprising. Again, you can see that Asia is particularly under threat from, for example, from rising temperatures, from accelerated pathogen life cycles, but also from typhoons and tropical storms and all those sorts of impacts that have impacts in shaping aquaculture production. So Again, in preparation for this talk for DAA 3 weeks ago, I thought, well, let's have a look at some of the temperature profiles in some of those countries. So what I did was I focused on 33 countries. I took the reference points, 57 reference points in those countries. I then looked at the 70-year data for each of those meteorological stations in those countries. What I then did was I then tried to extrapolate brand new temperature predictions, not based on the 1961 to 1990, but based on a brand new temperature guidelines for the current period. And just to show you, looking at India, so here this is the data sets by decade for the last 70 years. Oops, for some reason that didn't work. Okay, so what we have here, this is the 1961, 1990. This is the new 91, 2020. And then by using this, we can then extrapolate to move forward over the next 100 years to try and think about potentially how some of the temperature might change in some of those countries. So again, here we are in 2025, and as I just click forward to 2050, 2075, moving forward to 2100, it's not surprising that you see the color changes as we move to warmer climates in some of those countries. Okay, so moving forward very, very quickly, when we start to think about how the fish in those particular environments are doing, then you can see that we have, you can see here from this particular graph that once we start to move over 30 degrees, we're really starting to move away the optimum reproductive range for some of these fish. And then, of course, as we move into water temperatures over 40 degrees, really we're starting to move into the lethal range for many of those fish species, which means we're going to start having serious impacts on production. And then just taking all that information, so what I'm doing now is I'm taking all those temperature extrapolations with the optimal temperature, with the lethal range, and what this table is just showing you is these figures shown here in red. This is really just showing you when the major fish industries in that particular country will reach a lethal point, okay? I hope I explained that well. So just very quickly, what I mean here is, so for example, in Iran, we know that Iran has a major rainbow trout industry, about 190,000 tons. By 2082, water temperatures there in some of those regions will probably be approaching 22 degrees. This is going to be lethal for the rainbow trout industry in that particular country unless various strategies are implemented. Looking forward to others, so for example, in China, by about 2167, we know that the pond loach industry, currently around 367,000 tons. If water temperatures move to 30, that's going to endanger that particular industry. And then just looking to India and potential impacts there, then again, as we approach, hi Stephen, okay, I'll move it very quickly, okay. You can see again, this is just really trying to set lethal points for the industry. So thinking more about who survives the heat, well, we know that a lot of pathogens do much better than their hosts. Again, if we rank the pathogens by temperature, again, just looking at the lower part of this board, you can see that some of the pathogens do far better than the hosts in warm water. Those at the bottom are of particular interest. Moving very quickly forward, we also know there's an oxygen crisis. As water temperatures go up, for every degree that goes up, the oxygen tension goes down by about 0.13 degree. So this means we have stressed fish in warmer waters trying to do with pathogens which are thriving in warmer waters. So we also think about some of the facultative pathogens. Again, these facultative anaerobes, we know that they do much better in low oxygen water. They like 5 to 10 milligrams per liter as opposed to 21%. So again, you can see some of these most serious pathogens are really going to thrive in these very, very warm waters. Okay, so I'm going to skip past this, but this is really just saying about some of the costs of disease we know go far beyond just the mortality. And what I want to do is just in conclusion really, is just to say that we shouldn't just accept the inevitable. I've heard Rohana and Melba and Mohan talk about this many, many times before, but we can act now. We know that some countries, many countries already have good strategies in place for biosecurity, for addressing climate change. So very locally, we can think about things like using banana leaves to help cover ponds. We can think about solar-powered aerators. We can think about reducing stocking densities during warm periods. We can also think about a switch to different fish species in those warmer waters. As we step forward, we can start to think about the extent to which we begin to cover some of those systems. So we can start thinking about moving internally to temperature-controlled greenhouses. We can increase the degree of shading or structures over to try and control the temperature below. We can even, very crazily, we could start to think about using reverse osmosis to generate fresh water from seawater, which means there may be a point in the future when we can start to culture fresh water at sea. And again, we've seen, for example, lots of very innovative structures. For example, we now see oil rigs which produce massive amounts of fish far out at sea. We now have these massive long boats, again, culture systems, trying to move into situations where they're not competing for water resources or for sites. We have systems which have greater degrees of biosecurity. And then just very quickly, just thinking about, we can also have lots of innovation moving forward, for example, in the genetics. So, for example, we now can breed Nile tilapia, which can go lower. We've got Atlantic salmon, which can tolerate warmer waters. We also have tilapia resistant to Streptococcus pangasius, to bacterial hemorrhagic septicemia. In China, they've got some very interesting programs with carp resistant to KHV, and we also have some very interesting Indian initiatives where we have carps, rohu, which are resistant or can deal with infections of Aeromonas. So with that, I think I'm just going to say that there are a number of actionable insights that we can think about. Many of these are already in action. We can think about investing in predictive health monitoring systems, implement regional biosecurity protocols, develop rapid response networks, create industry-wide data sharing platforms. This is one of those sharing platforms. And also we can maybe even think about establishing disease insurance mechanisms where we can begin to have a biosecurity investment economically rational rather than being optional. And with that, I would like to close and say once again a big thank you to DAA, to the Fish Health Society, and to everybody here for listening, also to my co-authors. But thank you very much, everyone. Thank you.
Thank you very much, Andy. Very good insights, but I think more importantly, some focus on what we can actually do. And I think that's important. We might have time for maybe one quick question, if someone's got a burning question from the audience. That's good. Thank you very much, Andy. Okay, it's my pleasure now to introduce our next speaker, Dr. Sonal Patel, who is an internationally recognised expert in aquatic animal health, molecular biology and biosecurity, with over 2 decades of research experience across fish species, including halibut, salmon, cod, rahu, and she has led pioneering work in the host pathogen interaction, vaccine development, and early disease detection. Her career spans key roles in Indo-Norway collaborations, industry innovation at Vaccinova, and advisory leadership at the Norwegian Veterinary Institute. Dr. Patel serves on national and EU level committees for aquaculture biosecurity and animal welfare, and continues to mentor global researchers while shaping policy and standards for sustainable aquaculture. So, Dr. Patel, thank you.
Yeah, I would like to start thanking the organizers and the convener for the invitation, and a huge vote of congratulations. It's a fantastic organized committee. One may ask the question, why salmon in Asian aquaculture disease? I think it's much more about learning from the biosecurity measures that we have implemented in the salmon wrasse aquaculture and see how it can be implemented for the species here in Asia. So in 2024, we produced around 430 million smolts that were transferred to sea. And most of these smolts are now being produced in wrasse facilities in Norway. And the largest facility can produce up to 20 million smolts per year. And you can see on the map here, each and every red dot represents one facility. It can be sea-based facility, it can be land-based facility, and Andrew showed us a picture of offshore farming, and that is that red dot out in the sea. Why RAS? Well, from 2010 and onwards, this was an increasing trend in Norway, and this was mainly to reduce the seawater phase because of the delousing operations. Delousing is very strictly regulated in Norway, and by increasing the production on land, there was shorter period in sea, and thus also shorter period for delousing. And believe it or not, with Norway, with a lot of fresh water and seawater, when we started producing much bigger smolts on land, we also faced water limitation. And the production facilities, they produce up to 5,000 tons per annum, and the number of stockings is anyway from 3 to 7. Recycling aquaculture systems, I think most of you know it. It is being used for shrimps, at least in Asia. It's the main components. They are the tanks with the fish in it, feeding systems. There are mechanical filters, disinfection. Some producers decide to use disinfection in the internal loop, while others don't. And then the sequence of degassing and the biofilter may vary with the producer and the people delivering the equipment. And I would say that the bioreactor is the heart of the system. And there are moving bed or the fixed bed, and some producers in Norway, they actually choose to use a combination with the moving bed in between the two fixed bed plates. Does the RAS offer a clear difference between generation? According to the regulation, it does not, because you are reusing the bioreactors with the living microbial composition over the generations. And this creates a problem when you're trying to differentiate between the fish groups and the pathogens across the fish groups. Most of the producers would say the age of the biofilter is important, and it takes a long time to achieve a stable and a mature biofilter. And the hypothesis is that it outcompetes the invading pathogens, or does it? That's a question. We'll see, look at the case studies afterwards. And the industry is, of course, shouting us to the academics, saying there is a huge lack of knowledge about several of these factors, such as the survival and the establishment of the pathogens in the RAS, and also the methods to get rid of this. In Norway, we had a good period of using RAS for the fish aquaculture and the production of smolts. In the starting, we only had the production-related problems, and then came the pathogens. And we have seen the whole list of the bacterial, viral, and parasites in our RAS facility. So if someone says that RAS is proof of pathogens, it is not. We have all these pathogens in RAS systems for salmon. So this brought us to do the mapping of the reservoirs and identify the risk areas for the pathogen persistence. We did detailed interviews focusing on 4 main themes. Today I will just give you a few highlights of this, and did laboratory trials and commercial RAS facility surveillance. The report is published in Norwegian, but we aim to publish it in English in a peer-reviewed journal. And the main idea was to find what are the biosecurity practices in the industry. And the industry said, well, most often we just take the fish group out and do nothing, we just put the new fish group in. That is, according to us, a biosecurity level 1, doing nothing. And then you have the second level where you drain the water out, you might or might not reuse the water, and then you wash and disinfect your tanks. At least you're removing the biofilms to reduce the pathogen risk to your next fish group. The third level is doing both of the above, but you're also treating your bioreactor and the pipes and the water treatment system. And at the end, you're sanitizing, you're washing, disinfecting, including sanitizing your bioreactor. Additionally, several of the industrial people say they use a varying period of fallowing in between the fish groups. One of the main things that all the industrial people, at least in Norway, said is that hygienic design is of great importance because there are lots, meters and meters and tens of meters of pipes, angles and niches, dead areas, and this has to be accessible, washable, and drainable. And this is a major problem, actually. And the choice of material and the design is very important because if your material does not tolerate the soap and the disinfectants that you're using, you will create grooves where the bacteria and the pathogens will colonize. We have really old RAS facilities that are made of cement. There are a lot of pores and a lot of pathogen problems. And now the industry is in the movement of treating the surface areas of this to reduce this. The picture at the bottom is from a farm that has actually carried out sanitization. They had detection of ISA, which is a notifiable disease, and it is required by the food and safety authorities that you have to sanitize and take down the biofilter. What they experienced was that they went through several different steps of washing and disinfection and could not get rid of the pathogen. In the end, they had to disassemble the whole unit, including all the valves and all the pipes, and reinstall it all. And their main thinking was that the design, the RAS units are most often designed for the process and not for washing and sanitization. And this, you as a user, you need to ask for this because only then there would be improvement from the provider. Here is an example of the breach of biosecurity. You can see fish, many different sizes. These fish were flushed out from the piping and the bioreactors after the producer flushed anesthetic through the whole system to remove the fish out. And this, if these fish are infected, they would be constant source of infection to your new fish group. This happens when you're not sorting the fish, moving them to the new department. The pore size of your drainage is probably too small, so the smallest fish can pass through. Or during your washing or other operations, the fish can pass in, and they survive. The biggest fish here, the producer says, according to their production, that fish must have lived in the system for almost a year and a half or two. Okay. The production plan and intensity can also be a major problem if you want to implement your planned biosecurity measures. Think of the illustration here. This is a very intensive farm illustration, and think of a situation where the wellboat that is supposed to be transferring your smolts out to the sea does not or cannot come the day that you have asked. Then the smolts would be transferred to the sea maybe 2 days later, 7 days later, 10 days later, whenever the wellboat can come. That will create a backlog all the way back into your system. And then the biomass starts increasing, the stress starts increasing, and then you will have infections in the back over system. So in general, having a very intensive production and not having enough time for implementation of your measures or time for fallowing is not a very smart move. So I'll move more towards the laboratory trials and the commercial RAS facility surveillance now. Common to both of them is that we sampled the fish while the infected fish were going on into the system, and then the live fish that were placed into the system to check if the infection is passed on. Here we took the tissue samples, and in addition we took environmental samples of water and swabs and biomedia. For the processing of water and biomedia, again, you need to be careful. We had to use almost 6 months of optimization for the processing to be able to develop more sensitive methods to detect the pathogens in the system. So just taking the samples and analyzing them doesn't always work. You need to have more precision and optimization. Otherwise, you're doing a lot of tests and you're not finding, and you'll be happy. The swabs, we decided to take swabs from several different risk points, and this was in close collaboration with the fish health managers and the operation managers. We understood the operations, the design of the facilities at the commercial facilities, their take on the risks areas, and we as the academics, we were there understanding their operations and then identified those risk points. It's not just taking any point, because then you will not find it. In the lab trials, we carried out 2 lab trials, and one of them was with ISA, and the other one where we took the fish from a commercial RAS facility that had 3 different pathogens, 2 viral and 1 bacterial in the population, and transferred them into our lab facilities, which had single units with their own biofilter. Common to both the trials was that we had a period of biofilter maturation, a period for pathogen shedding to allow the pathogen to be spread into the system or even established in the biofilter or the biofilms. And then the third, when we did fallowing or certain measures after the source of infection was removed. After fallowing, we introduced live fish into the system to see if the pathogen can be transferred to the next generation. Additionally, we took some of the biofilters into small units of around 5 liters and carried out checking for the effect of just replacing the water, as the industry does this, or even ozonation. Here, there is a lot of information, and this I've just drawn up with my hands to represent a general average of 3 replicates, and I'm not going to go through all the details here. The most important thing is to understand that you need to know your pathogen, the characteristic of the pathogen, the survival of the pathogen, because here, as you see, Bronchiomonas that affects the gills. We expect this pathogen to survive for a very short period of time in the environment. And this is what we could confirm also in our system. In the main RAS tanks with the fish going around, we could only detect it for 2 to 3 days after the source of infection was gone. ISA, which is intermediate, we could detect it until 10 to 14 days, while IPNV, it is known to be a very robust virus, and we could detect it until the end of the trial. And this was also the virus that was passed on to the live fish, and 47 of the 60 fish were positive at the end of the trial. Ozone was the only biosecurity measure that we tested in the lab trials was really effective, although not completely, because we did detect at least 1 sample that was positive for IPNV. The commercial RAS facilities, you can see some of the components to your left. To your right, I'm just showing few pictures of the dead areas where there are biofilms. And when producers start cleaning, they forget to clean all these dead areas, and the pathogen can be adhering and passing on to the next. Lot of details here. The most important thing here is to understand that while the fish that had infection were in the system, we could detect it in all our samples. And once they had replaced the water and washed the tanks and removed the biofilms, it was all gone. So we could see a very good effect of the measure that the farm is following. However, we did not able to follow it with the live fish because they were already infected. The same farm, the same situation while the fish were infected, However, we could not see the same effect after they had done the same measure, the same people, same farm, different department, and this was surprised us. What happened here? We had detailed discussions with the farm, so many meetings, and finally we managed to figure out that there was an overflow from another RAS unit in the same department where some infected fish were going on. So it just shows very little that is required for you to contaminate all the facilities. The last case, HPR0 and PRV, again the same thing. We have a lot of positive samples, but here we could show the HPR0 in the biofilms. Again, due to the survival time, it goes towards the zero, but somehow HPR0 is a typical virus that shows it comes up and disappears, and that is what we could see, and we are still discussing with the farmer what happened during those days. So in general, if you want to have surveillance at your facility, I would recommend using swab samples. And remember, you're not doing this to support the authorities. You're doing it for your own sake, to be able to intervene and reduce the risks. Follow with the swab samples or maybe water samples, but the swab biofilter is very unreliable because you need homogeneous distribution. Also, it was not effective with the water replacement. Fallowing was effective for Branchiomonas and ISA HPR deleted, but not for IPNV. Same with the ozonation. It was effective for IPNV, but not completely. Again, know your pathogen and the characteristics of the pathogen. Finally, it was the same in the commercial RAS facilities where it is a very complex design with a lot of niches. We could not see a proper removal of pathogens with the top security, and we are in the process of planning to check with the last sanitization. RAS is ideal for many situations. However, it requires significant upfront investment, skilled technical management, continuous monitoring and maintenance, and again, once you have introduced a pathogen, it is very difficult to eradicate it. With that, I'll thank all the co-authors and the stakeholders and the private companies. It is a huge collaborative work, and the financing agency. Thank you.
Thank you very much. Excuse me, Dr. Patel. I often find it frustrating when you're advising research farmers about what to do in a situation of outbreak, etc. And this is very informative information, and know your pathogen. I love that. We might have time for one quick question if someone's got a burning question for Dr. Patel. No?
Okay, thank you very much for the informative talk. We are in Thailand. We also try to optimize this last system for the shrimp too. But we use this UV disinfection before the water going back to the culture tank. Can you give me a comments on that?
Yes, actually in Norway there are a few companies, like I showed, few uses UV in the internal loop while others do not. Some of them are succeeding while others are having some production related problems because of the byproducts that the UV can create. So be careful and check for the water quality, and some of them are even having nephrocalcinosis in the system because of this. So just check that you have proper water quality. Yeah.
Okay, may I have another question? We also, give and emphasize on this the microbiome balance in this culture tank and also the treatment tank after the dam. Have you in your facility, you also consider this balance of the microbiome in the water?
Yes, I actually had to remove a lot of slides. So we were actually doing a microbiome analysis at several RAS facilities. I have not included that in my presentation. And even like, for example, the ozonation, if you want to sanitize and use ozone, it can affect your microbial composition, right? So we have taken samples and we are actually analyzing them, and that's a story for another day. Yes.
Okay, thank you very much, Dr. Patel.
Thank you.
Yeah, thank you, Sonal. Now we have to introduce our third distinguished speaker. He is Dr. P.K. Sahu. He is the director of ICR Central Institute of Freshwater Aquaculture, SIPA, Bhubaneswar. He is a leading authority in fish health and freshwater aquaculture. He has a decade of experience in aquatic animal disease diagnosis, control, and vaccine development. He is a former national professor and ICAR national fellow. He has significant contribution in advanced molecular diagnostics. He has reported novel viral and protozoan diseases into the Indian aquaculture and pioneered research on the Indian major calves innate immunity. His current leadership spans genome editing for disease resistance and carbon neutral aquaculture. He is backed by more than 200 publications, 1 patent, and 5 commercial products, including development of a disease-resistant rohu. And he has the credit of the mentorship of several postgraduate students. And he is a fellow of National Academy of Agricultural Sciences and also recognized as the world's top 2% most scientists, top rated scientists by Stanford University. And I request Professor Sahu to give his lecture. Thank you, sir.
Thank you, Dr. Pradhan, for introducing me. Most distinguished chairs, keynote and lead speakers, Dr. Singh, Dr. Sonal, all my seniors, distinguished delegates. Once again, a very good morning to all of you and warm welcome you. And I must thank the organizers, DAA12, for giving me this opportunity. Of course, the title which I am going to present, it's 1940s title, you can say, but what I am going to emphasize here, where do we exactly stand? Dr. Mohan, yesterday he was speaking his 50 years of experience. Perhaps now we should think how to go ahead. We are discussing biosecurity, good aquaculture practice, where vaccine is one of the important component of the system. But we need to understand. So most of my talk may be repetitions to few of you, but what I would like to exactly highlight at the end of the day, the situation, what is prevailing in India, and also maybe in different parts of the world where aquaculture is going on, and how we are going to address tomorrow. And my co-authors, Dr. Megha and Dr. Makesh, both are here. So what I was mentioning with a brief introduction to the topic, I will give a brief overview of the disease scenario and what is the status of vaccination in the whole world, as well as where do we exactly stand and what are the opportunities. And I will give little bit emphasis on the Government of India initiative in this particular regard and how to go ahead on this vaccination process. As already it has been mentioned, I will not go into the details. Tomorrow is the world is going to see much more production from the culture rather than capture. But on the other hand, as Andrew was mentioning, it may not be 10%. It may go up to, we do not know how much it will go, up to 30% or what. The major loss we are incurring because of the diseases, but still then we are thinking for the intensification. we are not thinking of non-fed species aquaculture, although we are thinking to some extent, but nevertheless, we are giving much more emphasis on intensification. As already Andrew has mentioned, we have direct loss, indirect costs, and threat, and how much loss we are incurring. If you think in terms of mortality or reduced growth, which has never been taken in many of the disease conditions when we are estimating loss. So that is very important. And also the increased use of antibiotics, chemicals, residual problem, or how it is affecting the product quality or the production cost or export market. These are the things down the lane we never, in fact, except mortality, we never calculate or take into consideration. On the other hand, it is very well said how climate is going to influence the future scenario. That is very important. And the quality of water which will be available for us tomorrow for aquaculture, that is also a big challenge. And with the routine evolvement of pathogens, and also how we are going ahead with the unsustainable farming system, which will be discussed maybe tomorrow or day after with regards to One Health or AMR. So all those parallel challenges are there. But one interesting paper which says, you can see the relations, this is with regards to Asian cage culture in East and Southeast Asia condition 1986 to 2020. You can see the number of articles on fish diseases, how it is increasing. And if you will see the scenario in those articles, most of the reviewed papers, they have reviewed on the parasitic diseases. And then next is bacterial diseases. And again, co-infections, how it has been emerging nowadays. I am not going into all those details of this article. On the other hand, you can also see how many viral families it is available in GenBank, accession numbers are available in GenBank, how many viral families are coming into aquaculture system. It will be a big challenge for tomorrow to address how we will go ahead, whether only your vaccine is going to solve the purpose or not. And again, as I was mentioning, the co-infections, whether it is with parasites, with bacteria, bacteria with virus, virus with fungus. So it is also becoming a big challenge. I do not know about other parts of the world, particularly with regards to warm water species. It has been a big challenge. Nowadays, not a single pathogen which is causing disease in any disease conditions. If you see the scenario in case of shrimps, we have been discussing BMNB, MBB in 1970s, WSSB 1980s onwards, and YHB, TSB in 1990s, again INB, CMNB 2000 onwards. But now we are discussing multiple infections, including EMS, co-infections, EHP and Vibrios. It is also same condition if you will look into the freshwater fish diseases in India. This is an example. When we initiated the surveillance program, this is data of 2-3 important states, including Odisha and eastern part of India. The parasitic diseases were much more prevalent, along with few mixed bacterial and parasitic infection. Slowly we are moving to, although parasitic diseases are there almost 50%, then 17% bacterial diseases, but mixed infection 27%. And within mixed infections, both bacterial, parasitic, viral, all those are dominating. So if you will see, we are describing in every 3 to 5 years, one new disease are emerging. But when we have initiated surveillance program, before surveillance program started, we have only one viral disease, 2005. It was being detected in sea bass, both in fresh and brackish water, beta noda virus. But you just see, 2014, we reported CYHB2, 2015, Rana virus, 2016, CEB, 2018, TILB, 2019, RSIB, 2020, ISKNB, LCD, And 2021 rhabdovirus, snakehead rhabdovirus, 2022 KHB, 2023 TIPB, 2024 microvacuum Golla virus. So every year new viruses are being reported. Of course, one of the major reasons is the strong surveillance network which India is implementing. But so far we have not come across major viral pathogens in Indian major crops. Perhaps that is one of the most important reason this carp culture system in India is surviving and growing. Today, it is not the Snezikos model what we discuss, it's not limited to host pathogen environment, rather we are much more discussing on the susceptibility and genetic predispositions as well as also nutrition of the host. Coming to the pathogens, we are more discussing on the co-infections, emerging and re-emerging challenges, resistant microbes, and environment is not only restricted to the water quality, rather climate change and sudden water quality shifts because of the prolonged weather fluctuations and also multiple stressors. All these conditions, rather they are governing the scenario. So coming to the vaccination, which is being considered as one of the most important steps in preventing diseases, you can see the global market which has been predicted by $290 million by 2025 and by 2030, $617 million industry it will be. And you can see the global trend. Most of the vaccine segments, vaccine sectors, they are producing bacterial vaccines. And you can see the bacterial vaccine itself, by 2024, the market has been anticipated for $30 million. And within the bacterial vaccine, you can see the highest market share is by inactivated vaccines mostly, inactivated vaccines. And mostly salmonid vaccines, if you will see, they are growing at 8.1%. Of course, many countries, those who are practicing aquaculture, they are also doing research on vaccine aquaculture. They are doing research on vaccine aquaculture. But still then, many of these vaccines, they have not entered into the commercial segments. I am not going into all those details, but these are the countries which are mostly practicing vaccines in aquaculture. Just morning, I was discussing with Dr. Sonal how they are going ahead with 7 diseases with a single prick for vaccinating for against 7 diseases, but there are several concerns also she was mentioning. So I am not going into all those details. Rather, I will say the most of the vaccinations which have been practiced, it is with regard to either salmonids, then followed by tilapia or sea bass and sea bream and trout, but carps, it's very less amount vaccination is being practiced. There are several key players. I am not going into emphasize into whether who is number 1 or 2, but most of the market has been taken by Zoetis or Merck or Pharmac and other companies which I have listed here. You can see most of these companies, they are mostly producing the inactivated and injectable form of vaccines. Inactivated and injectable form of vaccines or bacterial vaccines, and some are producing also immersion-based vaccines. But the scenario is, if you will see with regards to bacterial vaccine or viral vaccines, the case is, in case of bacterial vaccine, most are going for injectable and either killed or subunit vaccines. If you will compare with the viral vaccines, mostly they are going for immersion or bath-related vaccines compared to injectable vaccines. So this is the status with regards to world scenario, and with regards to the research on world, what aspect it is now moving. Now we are giving much more stress on different types of either subunit vaccines, mRNA-based vaccines, recombinant vaccines, or edible form of vaccines, or some of the nano-conjugated vaccines, or in case of some of the parasites vaccines also, where we are going for subunit-based vaccines. I am not going into all those details, but industry is much more working with regards to adjuvants, because it has been seen that adjuvants are playing a big role. I will just give an example here. I am not showing the slide. We are working a lot on Argulus vaccine. The fish which is showing poor immune response to a pathogen like Argulus with regards to inflammation, they are much more susceptible. So inflammation plays a very crucial role with regards to protection. So in case you are developing some kind of molecule which will work like adjuvant and it will induce inflammation, that will definitely give a better protection in comparison to any other adjuvants. So that we have seen. On that basis, that has made a basis for developing some kind of vaccine for parasites. Nevertheless, you can see the cytokines, a lot of work has been done. And some of these are pro-inflammatory cytokines, how they have been used as adjuvants. Some of the nanoparticles, a lot of work has been nowadays, it's going on to use them as adjuvants, CPG motifs, and some of the pathogenic or probiotic compounds which have been used as adjuvants. Besides some virus particles. Coming to the Indian scenario, till date, as Dr. Jana Saab was yesterday mentioning, till date we do not have a regulatory guidelines in India. We are doing research since more than two and a half decades in India with regards to vaccine. We have developed couple of vaccines and also we have commercialized some of the vaccines, but it has not been practiced till today in Indian aquaculture system. Some of the bacterial vaccines and one viral vaccine which have been developed by 3 of the fisheries research institutes, some are in pipeline, and one vaccine recently we have released for the Argulus parasite, Sipha Argovax I, which is a peptide-based vaccine. It is giving excellent result and it will be very shortly coming into the market. And there are several other vaccines where we are working as a proof of concept. We have worked on bicystonic DNA-based vaccines for TADA. So many outer membrane protein-based vaccine. Madam Karuna Sagar is here. They have also worked on different aspects of outer membrane protein-based vaccine. Some multivalent vaccines also, inactivated vaccines for multiple pathogens, some parasite vaccines. I am not going into all those details, including oomycete. Dr. Pradhan is here. They have worked on inactivated germinated juice spores, how it has been used as an candidate in oomycete vaccine development, and also with regards to vaccine viruses like beta noda virus and cyprinidae herpes virus, and also tilapia lake virus. We have been working, we have developed different vaccine formulation to go ahead, and also we are working on next generation vaccines like RNA based vaccines and edible WSSB vaccines, as well as also microRNA based improved delivery methods. But there are several challenges. I will not describe all those challenges, including regulatory bodies, whether it will be economically viable or not, off-target effect as Dr. Sonal was mentioning in the morning, environment or leaching aspect or delivery uptake, all those challenges are there. But what I would like to emphasize here, we have to think of the cost of the technologies when we are going ahead with the low valued species with regards to vaccine development. When we are producing huge amount of carbs, so those are low valued species as being considered, how we will go ahead with the vaccination strategy. And also we have to look into the novel delivery systems, we have to look into the adjuvants and regulatory managements. But what I would like to emphasize, Government of India has already taken initiative. One of the major initiative is the surveillance program which is going on to address what are the important pathogens, where we should work and what we should address. And another important program is going on our ICR system to develop vaccines and diagnostics, that is ICR CRP on vaccines and diagnostics, which encompasses One Health. In fact, it is addressing both all plants, animals and fishes, where so many technologies have been developed. But what I want to emphasize here in my last slide, that most of the time we are getting multiple etiological agents. So how many etiological agents you will target through vaccines? If in today's scenario, in a single case, when there is mortality, you will get 4 or 5 pathogens, even up to 7, 8 we have reported. All these are pathogens, they can individually cause mortality and they are also causing mass mortalities. So we have to think into all those factors. And most of the cases, suppose TIPV, it has started, it caused mortality, huge number of mortality. Within a year or two, now it is almost endemic, mortality is not there until unless stress factors are not there. Once there are stress factors, then only mortality is happening. Again, most important thing, while we are debating on the diversification, in fact, we have gone to 12 species culture system in a single pond. So how much devastating it will be, I do not know if you will think in terms of disease. How many species you will go for developing vaccines and study vaccinology for all those species. And again, diversifying the systems. She was talking about RAS. We are going for short generation period when we are going for bioflux system, raising seeds. So how we are going to implement? For example, in our institutes, we are working on 30 species, freshwater species. 30 freshwater species. We have breeding, seed production, culture technology. So you have to think how you are going to face the challenge of disease scenario if you are not addressing properly and you are not prioritizing. And just I was mentioning, the viral signature what we are getting, every day it is increasing. So how you are going to address tomorrow with regards to vaccinology, so that will be a big challenge. So with this, I must thank all the funders, all the institutes, and the research fellows, scientists, and finally my farmers friends where we are doing our field trials. So I must thank everybody in this vaccine research study. And with this, thank you very much for giving me this opportunity. This is our farm and building at Central Institute of Freshwater Aquaculture, Bhubaneswar. Those who have not seen, this is one aerial view. Thank you very much.
Thank you, Dr. Sahu. Maybe we can take one quick question before tea break. Yes.
Yeah, thank you very much, Dr. Sahu. I think one of the biggest challenge on the adoption of vaccines, especially in the region, is on how to, deal with the different government regulations in the registration of vaccines. We have a lot of research in the region. We have some pharmaceutical companies already developed vaccines in the region, but it was not adopted at the farm level. You mentioned one, the cost is so expensive, and most of the fish species here are low-value fish. So comparing to salmon, which is a high-value fish, which is where vaccine was really successful, especially in reducing the use of antibiotics. So we have a lot of vaccines, but this cannot reach the farm because of these government regulations in the registration of vaccines. And farmers cannot use it unless it is certified or approved by the government.
Thank you very much. In fact, you are also mentioning how to go ahead. In fact, regulation, that is very important. And in fact, India is actively working on it. Hopefully, as Dr. Jana was mentioning, maybe within 2-3 months, if we are clearing, the guidelines will be cleared, then definitely Government of India is going to promote on a large scale for use of vaccines at the first instance. If Government of India is going to promote, perhaps they will never think about the cost. So even if we are going ahead with low value species, we have to prioritize what are the vaccines which we should go immediately with those species, whether it is bacterial or parasitic, which are being challenged in carp culture systems. So we have vaccines ready, the research angle and commercial production. Suppose, for example, Indian Immunologicals, they are here, they have already produced, it has been all the safety potency testings, those are all are over. We are waiting only when government is going to clear the regulatory guidelines. Once it will be cleared, perhaps it will be taken up in India. In fact, although most of the vaccines you can see, salmonids and others, they are being used, which are not the species of culture in India. So importing, absolutely it has not been thought of in that angle.
Okay. Thank you, Dr. Sahu, for your presentation. And I'd like you all to put your hands together for our 3 presentations today in this section.
Thank you.
It's a
Thank you.
very informative talk. Now, thank you everyone for your indulgence. We're running a little bit behind time, but I think it was important to scene set for our future presentations for the rest of the morning. So we're still going to keep you to time and start at 10:40. So rush, get your morning tea, and even bring it back with you as we start the next session. So.